In this video, I want to talk about cones. Now, we've seen cones come up in a couple different places already as we were looking at hyperboloids. These are very closely related to hyperboloids. In some ways, I think of them as a degenerate form of both a hyperboloid of two sheets and a hyperboloid of one sheet. It's the transition from one to the other, as we saw in previous videos. Right? Now, the basic equation here, this is with no shifting, x squared over minus x squared over a squared minus y squared over b squared plus c squared over c squared equals 0. This is made it to look like an hyperboloid of two sheets with the two negative signs, but it really is both, because if you multiply both sides by -1, it turns all the minuses into plus, and that plus into a minus, and the 0 times -1 is still 0. So this makes it look like a hyperboloid of one sheet, but it's neither. It's both. It's in between. It's the thing in between. Now, how do I know that the graph of it looks something like this? Well, first of all, the way I have this set up is the z is the odd variable out. X and y both have pluses and z has a minus, or the other way around. So this thing is centered on the z-axis. Now, how do I see these circles or ellipses, whatever they are, and the straightness of those sides? Well, here's how that works. So let's start with this equation right here and look at traces in the different planes and things. So the first trace I want to look at is the xy plane, that is with z equal to 0. So if I plug in z equals 0 right here, that term just disappears, and we end up with something that looks like this. Well, this is an ellipse in the xy plane, but with a 0 over here, it's actually a radius 0. It is the only way you can get, this is definitely a positive, or at least non-negative number, and this is a non-negative number, and the only way you can get two things add up to 0 is if both of them are 0 in the first place. So both x and y have to be 0, and the only point that satisfies this equation is the point x equals 0, y equals 0, and of course you've already had z equals 0. So this is just a single point at the origin. That's this thing right here, which we call the cone point. Okay. Now, take a look at traces for other values of z. So I'm going to plug in z equals, pick a number, any number. Well, I'm going to actually pick a spectral number, not any number. I'm going to plug in c here just to make things work a little more cleanly for me. So I'm going to plug in z equals c, and so I get the c squared over c squared here, which is just 1, and then move it to the other side. And I'm looking at x squared over a squared plus y squared over b squared equals 1. This is an ellipse that moves, center at the origin, back and forth, a in the x direction and b in the y direction. So that's kind of nice. And if I pick any other value of z here, that this will not be 0, and you move it over, and then you can divide by it. And what you'll have is you'll just have scaled up or down versions of this ellipse. The relationship will still be the same. Well, it'll be similar, right? The a and the b will still be there, but you'll also have that divided by whatever this number turns out to be. Of course, in the denominator, they'll be multiplied because that will be down there with them. Okay. So I have, for different values of z, I have either a point or I have varying sizes, varying ellipses of different sizes, right? Now, let's look at the xz plane. So if I plug in y equals 0, plugging it into there, I get this. Now, this is what? It looks kind of like a hyperbola because of the minus sign there, but it's not a 1 over here. And I can't make it a 1 because I can't just divide by 0. So what I'm going to do is I'm going to notice that, hey, this factors. Now, of course, it would factor even if there was a 1 over here, but there's an importance here of this being 0. So this is a difference of squares, so it factors into x over a plus z over c and x over a minus z over c. And because this is a 0, and this is only because it is a 0, I know that the only way a product could equal 0 is if one or the other of the two factors was equal to 0. If this was a 1 over here, I wouldn't be able to say anything because, give me two numbers that multiply to be 1. Well, 1 and 1 work, but 7 and 1/7 work, and, a million and 1 divided by a million work. It just, with it being anything other than a 0, you can't proceed. However, with a 0, you know that one or the other of the factors has to be 0. This is the equation of a line. Z equals minus C over A times X. This is the equation of a line. Z equals C over A times X. So in the in the XZ plane, the trace is two intersecting lines, right? These two lines both go through the origin. So it's this X, right, in the XZ plane. Likewise, if you look at the trace in the YZ plane, so you plug in X equals 0, there's a similar thing that happens, and you get two lines again. So when I'm up here looking at this here, that is in the, this looks like the XZ plane, you've got a line running down this way, and you've got a line going up that way. Those two intersecting planes, so intersecting lines. And then the YZ plane, you've got a line that's running down this way, and a line that's going up this way. And that those are nice and straight. They are lines. This is a cone. Now, let's take a look at one example here, starting from an equation. When I look at this, I don't immediately see that it's a cone. What I see is that I have x squared, y squared, and z squared all there, so it's either going to be an ellipsoid or a hyperboloid or a cone. Some of them are positive and some of them are negative, the coefficients in front of the squared parts. So it's not an ellipsoid, it's going to be a hyperboloid or cone. Now, the minus 11 over here doesn't tell me anything yet, because this other stuff here is saying there's some shifting involved, and so I'm going to have to complete the squares to see what all's happening. So, get the x's together, get the y's together, get the z's together, and then complete the squares. So I've got a factor out of 4 out of the x's, I got a factor out of minus 1 out of the y's, and a minus 1 out of the z's. So that's what I did. And then inside the parentheses, complete the square. So with a 1 in front of the x squared, I can just cut the 4 in half to get 2, square it to get 4. So I'm adding on 4, but I'm not really adding 4. I'm adding 4 times 4. So I'm going to compensate by adding 4 times 4 on the other side too. Likewise here, inside these parentheses, there's a 1 in front of the y squared, take the 2, cut it in half. That's 1, square 1. I'm going to add a 1 in there. But I didn't really add 1. I added negative 1 times 1. So I subtracted 1 from the left side. I better subtract 1 from the right side. Likewise here, there's a 1 in front of the z squared, so I can just take the 4, cut it in half to get 2, square it to get 4, add a 4 in there. But I'm not really adding 4 because there's a minus sign up front. I'm really subtracting 4 from the left-hand side, so I'm going to subtract 4 from the right-hand side. And what happens is this turns into a 0. Now, if this had not been a negative 11, all of the work I would have done would be exactly the same. But this would not have turned into a 0. This would have turned into some number other than 0. And I would now divide by it and see an hyperboloid of either 1 or 2 sheets. If it turned out to be a positive number, then these two negatives would stay negative, and I'd have 2 sheets. If it was a negative number then here, when I divided, then all the signs would change, and I'd have an hyperboloid of 1 sheet. But it's a 0, and I can't divide by it. So what I have here is a cone. And dividing everything by 4 to get this out of there, I see this. So what I have is a cone centered at 2, 1, negative 2. That's got some ellipticalness and some circularness. It's centered around around the x-axis, because this is the odd one out. Let's see if I can draw this. Here we go. We're going to try to draw this. Here's my axes. So if x is equal to 2, then what I have here is just a point. So actually, we already said this is centered at 1, 2, 2 in the x direction, 1 in the y direction. So over here, and then down 2. So down here, 1, 2. So it's centered here. Draw another coordinate system in here. And so centered around this line, there's the cone point is right there in the center. And then what happens? in the XZ plane, I've got a parabola, sorry, got a hyperbola that opens up more in the Z direction. So it opens up more in the Z direction. So it's going up kind of steeply here. Okay, so there's ellipses like that. Oh, but in the Y direction, it's the same as the Z direction. So actually, these are circular cross sections. Ah, wow. So I've got circular cross sections, front and back. And then right, parallel to that line through the middle there, which is this line right here. Really bad drawing. This is why I like computer graphics. But good drawing or bad drawing, I've got a pretty good idea where that is and what orientation it has by looking at this. There's circular cross sections for different values of x. Then I say circular because those numbers are the same on the bottom. And going down to a really small circle at x equals 2. Right. So there is some cones. Now, there's one other degenerate form that we saw that I want to talk about, and that is a cylinder as seen as a hyperboloid. So let's take a look at that real quick. So here is the equation of a hyperboloid of one sheet, or maybe it's a cone, depending on what D is over here. I have it written a little differently. Rather than x squared divided by a squared, I just have x squared times a number, right? And all right, likewise here, it'd be y squared times a number. And what I want to do is I want to say, I'm assuming here that D is not 0. And what I want to do is I want to let this thing go to 0. So let C get smaller and smaller and smaller. And what happens is when it gets to 0, right, when C gets to 0, then the Z squared disappears, and now we're in the situation of having a cylinder because one of the variables isn't in the equation. And what's left is the equation of an ellipse, right? So in the xy plane, which usually I draw the xy plane down here, so in the xy plane, I would have an ellipse that goes back and forth. D, the square root of D divided by A is what it would be. And likewise back and forth in the Y direction by B divided by D. Other way around, D divided by B, square root of that. And so I'd have an ellipse there in the, well, if that's a 0, right? In the xy plane, this is what it would look like. Whether that's a 0 or not, I mean, whether C is a 0 or not, when you plug in Z equals 0, this will be the cross-section in the YZ plane, in the XY plane, right? But as C goes to 0, what happens is the flare of the hyperboloid of one sheet gets less and less until finally it's straight up and down. Right? Now, an interesting thing here is that it also goes the other way. That is, I'm thinking of C as being a positive number heading to 0. So it's going to 0 from the right-hand side. Right? So I'm thinking of this as subtracting a positive number. But if C then becomes a negative number, that this flare goes the other way, and that cylinder actually will turn into a big old ellipsoid. So you've got this thing that's flaring outward and then comes in to be straight up and down, and then it starts to flare inward, and your hyperboloid actually turns into a cone, not a cone. Hyperboloid turns into a cylinder, which then turns into an ellipsoid. Really pretty cool, just by varying this C value here. So the cylinder you can see as either a non-flaring hyperboloid or a really long ellipsoid. Anyway, there's a couple of what I consider degenerate quadric surfaces. They're straight as opposed to curved like ellipsoids and hyperboloids. We have one more quadric surface to cover, and that is the paraboloid, and we'll see that in the next video.